connected.
For New Zealand, as the Americans took a bonus point into the match thanks to winning the first round of qualifiers. So the scoreboard shows a 3-race lead for Hitler and Hungary.
Interesting boats, aren't they? Complete change from a decade ago, I suppose. All right. So it used to be that the boats looked a bit like this. This is KZ1, which is New Zealand one, which is a boat that now sits, or doesn't sit, it's actually in Auckland Harbour in New Zealand. This was taken last year. These boats used to be like in the America's Cup, and apparently these ones were a huge evolution over previous boats, where it's not a particular size of boat, it's like 23 meter boats or something, but the 23 meters is some strange combination of dimensions that has to add up from the beam and the length and the height and the sail area or something. I'm not quite sure, but certainly this evolution to what you just saw on the YouTube video is really quite stark, I think. Yeah, good way to spend an afternoon, right? Yeah, fine. All right. And we won't look at another one, but and what else we got here? This is perhaps a bit more routine. See if this one works.
This is what $128,000 and some might argue a lapse in sanity can buy you. MS Watersports has created the Jetlev Flyer. This jetpack, or personal propulsion device, can reach top speeds of a little over 40 miles per hour and reach an altitude of about 50 feet. Unlike other jetpacks, this one can keep its pilot aloft for hours and fly for about 186 miles. The reason is that this one leaves its fuel supply and power plant on the ground, or more appropriately on the water. That's it there, floating in the little pod on the right.
That's
a
right.
4-stroke power plant that the German...
Yeah. So you see it's untethered. It's got some kind of power plant behind it that pumps water up into the backpack, and then you squirt it down as a reaction. So it's like a jetpack that's powered from an umbilical. I don't know. They'll probably tell you what they cost. They cost $20,000 or $60,000. No idea, but it's kind of an interesting item. Apparently they traveled with one to Catalina Island, offshore LA. There's the islands offshore LA that are characterized in that classic movie, Jack Nicholson movie, too old for you maybe, but it's a classic movie with Jack Nicholson in it, Chinatown, I think, right, which documents the water crisis in LA and how they got water from the Owens Valley and how nefarious activities were going on to do that. And finally, before we get down to actually do something useful today, I think this is an interesting behavior as well. So I think from the late actually it does have a date on it. I can't remember what the date is. You can tell by the livery on the airlines that United certainly doesn't have that livery anymore since it's merged with Continental. But it shows that to get something that weighs, I don't know, hundreds of tons, I suppose, for a 747 or an A380, to get something like that off the ground, you need to have a lot of power, a lot of thrust to be able to push it through the air to get lift on the wings. And so I think this is a health and safety video to suggest that you don't randomly drive behind planes when they're taxiing or taking off. So you'll see what happens in a sec. You'll see the truck's empty. So, and I guess they drag it out of the water. I'm pretty sure that's San Francisco international airport. Oh, and it's a staged demonstration. That's surprising. I thought they always get towed in front behind airplanes. And so each of these really make the fact that what we're moving on to talk about now is not so much static fluids as we have so far in both pressure at a point, pressure distributions, and also in terms of accelerating fluids. But we'll talk now about moving fluids. So this is weeks 4 and 5 proper. I will say something also. You should have got an email announcement. Hopefully you're on Canvas for email announcements, so you should have received this at midnight. The reality is that we're coming up a week from now to our midterm, and as promised in our schedule, online now there's a review video, and I won't go through that today. Apparently 8 people have looked at it. I bet you 4 of those are me. Sorry? Okay. But you'll see on there some information about the exam. Probably what you might do is look at that email, look at the video, and bring your questions on Friday, and we can briefly address any issues you have. It's a closed book exam, nominally 90 minutes, but you can stay from 8 till midnight. Bring a calculator, make your own equation sheet, print it, do whatever you like, and a pencil or a pen to write with. You don't need any paper. That'll be all on the sheets if you've seen, if hopefully you looked at the exams, as you were encouraged to do on the first meeting. The topics cover up till Monday, weeks 1 to 3, and also Monday of this week. And the individual questions, at least for the scheduled exam, are these 3 questions. 3 questions, each worth 110 points. 100% is 300 out of 330, so you can get actually 110% should you get everything right. Same as other exams. Look at the video. What this gives is a summary of the equations you need to bring with you and know how to use to be able to do well on this test. And so I encourage you to look at that and bring any questions on Friday, and we'll briefly talk about it. I don't want to talk about any more about, is this on it, is that on it, because you have what you have. And so you'll see as you roll through this, as he drops his pen on the floor, that basically it goes through and summarizes a bunch of expressions that you might need to be able to do those 3 questions on those topical areas that are included. Some topical areas aren't discussed. You can probably make an assumption about that they might not turn up. And so that's up to you. So I encourage you to do that and to bring any brief questions we have on Friday. Okay. Any questions now? Go ahead, quick.
It's more of a, so when you have an air pressure in a pipe or a tube, and it's going towards...
I meant about the exam. What, it sounds like a personal question. Do you want to ask me at the end of the class?
Yeah, sure.
So fine.
It's like an exam question.
Fine, yeah, fine. Well, yeah, use the resources available to you. The TA is defined, Savern defined as hours. GHOW's here. If you can't make the hours that Savern puts together, then make an appointment with GHOW. Come and see me if you wish. I might not be as friendly as those guys, but you're certainly welcome to try. Yeah. I would say that, my advice is that in the same way that the assigned questions aren't a good indicator of doing well on the exams, go back to the exams. If you see from those 3 questions the outlines of them, you can guess what those are. Go and look at previous exams and see what type questions like that have looked like, and work to that. They're all solved, so you should be able to work it out. I'm pretty sure that all the answer sheets in the exams are correct as well. They've kind of stood the test of time. May not be. I could be proven wrong, but I think they are. So, okay. All right. Hate to bring up such a painful topic, but it's a reality for us, I think. Okay, and so yeah, so you know where we are with this. This is where we are today. We're on the 12th. It's certainly posted already. It was posted yesterday, actually, and it's on this coming Wednesday. Okay, right. I don't have anything else to really say about that. All right, so let's get back to the matter at hand. Okay, so we've said before that we're making this transition today from talking about static fluids, which in the last instance were accelerating, and we know some behaviors for those fluids. If they're not accelerating, we know that this is true. If they are accelerating, we have to take account of those accelerations to, for instance, define what the free surface looks like, and, for instance, say how pressures might change in the y direction. And be able to manipulate that in some way. And that is the behavior we have for going typically up in a fluid or across in a fluid, as defined by these coordinate directions, which we've always defined in terms of x and y horizontally and z vertically. And we also talked a little bit about what happens in terms of rotational equilibrium. And so the idea for that is that we have some kind of weight which is being held, and it can be a fluid, but you could imagine it could also be some kind of tether, and it's moving at some rotational velocity. And because this velocity is a function of both speed and direction, and the direction is changing as it works around the arc, there's an acceleration in this. And in the same way that when we use F equals ma to be able to define these expressions, we also use F equals ma, but this is centripetal acceleration, to define this behavior. So there's a common theme in that. Therefore, since we know that if you look along this line, there has to be a tension that's applied, and we did an example at the end of the last period on this U-tube manometer, which is spinning, and as it spins, you get a low pressure within the base of it, because the sides are pulling apart, and it's having to pull the fluid back in, and as you spin it faster and faster, it will ultimately cavitate. There has to be a force that's applied here. So presumably that means that as you go across this boundary, there's a change in pressure. And we kind of know that because when we looked at this particular example of maybe a fluid which is spinning around a center line, then we thought that the distribution of the free surface should look like this. And if the distribution of the free surface would look like this, then merely by going down from the surface of this fluid to the base, we see that under here there's a different pressure at the base of the tank here than there is here. And so there's a change in fluid pressure as we go across here. And so these are nominally rotating fluids, but there's a direct analogy in terms of what we'll talk about now, in terms of fluid dynamics, and the videos we looked at, especially in terms of the America's Cup one, and that is that the sail in the America's Cup is something that is acted on by a fluid, a gas, air, and it basically acts as an airfoil to be able to drive the boat forward. And when the twin hulls or triple hulls of the catamaran or trimaran come out of the water, those are on keels which have airfoils on the base of them, which has the same behavior of lift as an airplane wing, and brings the hull out of the water, so you have very little drag resistance on the system. And so clearly a very important structure for us to be looking at is something, if I can draw it well, hasn't stopped me in the past if I can't draw it well, is something that looks like an airfoil. And so what we'll find out, basically when we're talking about fluid dynamics or moving fluids, is that we can imagine a streamline. And you know or can imagine that if you have a streamline which impinges an airfoil, it gets separated above and below. It rejoins itself as it comes out. You can imagine if you put a tracer, a smoke tracer or something around this airfoil, then you'd get some different behaviors that look like this. So these would be the tracks that a particle of smoke might make as it got driven downstream. And so there's something a little bit similar to the things that we've talked about in terms of accelerating fluids, in that certainly the fluid is undergoing a uniform acceleration if it's within a tank. What happens within a fluid around an airfoil is that the velocity we have that's upstream, maybe at 0.1, along the streamline, is not necessarily the same as the velocity that we have downstream. So if it's not the same velocity, then it's not the same as a tank merely translating across in front of you, but this one's going faster and this one's going slower, and so they're getting spaced a different length apart as they go downstream. And so that is now the new condition that we would like to account for. And so if we look at being able to represent these behaviors, actually we can use the same expressions that we've developed for flow both along a streamline and perpendicular streamline are actually directly analogous to these two behaviors. And so if we look at the linear accelerating system, that's the same as flow along a streamline, because basically it's going from one velocity here to another velocity here. It's accelerating, and so if it accelerates, there has to be a change of force that's applied to it. You're acting against inertia, and therefore you have to expend some energy to do that, and that energy is a trade-off in terms of the pressures or the potential energy that you have in the system. And those are the three components of the Bernoulli equation, which we'll talk about today. But also there's a direct linkage in terms of rotational behavior, and that is that in this geometry that we have, you could imagine also that as you go from, say, this point here, normal to the streamline, then the question is, for instance, how does pressure change as you go in this direction to this point, V3? And it's not so different from having a fluid which is spinning in some way. You can't see it here. They look like they're going parallel to each other. But if you imagine a vortex that is spinning around, so there's some centripetal motion, you'd expect that you go from this point here to this point here. It's not different from making a transition across a streamline. So all I'm doing is setting the stage in the fact that our work that we've done already on accelerating fluids in static tanks has a direct bearing on what we'd like to talk about in terms of moving fluids. And of course, these moving fluids rely on what we'll call is the Bernoulli equation. And you probably know it because we talked about it the first time we met. And the one that is along a streamline is pressure divided by unit weight of fluid plus the elevation plus the inertial term, v squared over 2g, equals constant. And we've used that. But what I want to do first is actually recover that really from the things that we've talked about already. And so let's make an attempt at least to derive the Bernoulli equation. And we could spend pages and pages doing this, but let's not. And let's remind ourselves of kind of the geometry that we have for pressures within a fluid. So what we could do relative to this coordinate dimension, if you think of 2 points, an upstream point and a downstream point, we know that the behavior that we have at any particular little cube of material that we have in here that represents a different volume, differential volume, we can write in terms of F equals ma. And at least in terms of along the streamline, parallel to the streamline. So this is streamline parallel, this is streamline kinds of behavior. And so what we could do is we could try and figure out exactly how we might want to rewrite this acceleration term. We know that acceleration is equal to the rate of change of velocity, in this case, in the z direction. What we could do is we could multiply that by 1 in terms of time, in which case we have rate of change of velocity with time and rate of change of time with occasion. Okay, no. Can that? This is not location, right? This is time. So we can multiply, t's and z's look the same. Multiply by 1. Rearrange that in terms of to put the z under here. Right? If we look at what these terms are, this is merely by definition a velocity, and this is a location as we travel downstream. And we can actually write this as equal to a half rate of change with z of v squared. And so you can confirm for yourselves that you can get this equation from this just by differentiating it with respect to velocity, I guess, rather than anything else. So if we think that's the case, then we basically have, by resubstituting, we have this expression here. We have dp dz. I'm just going to write this, the equation we have above, minus rho g minus density times a half rate of change with z of v squared, which is equal to 0. We could rewrite that by multiplying through by dz, in which case we end up with minus, let's write it as not an ODE rather than a PDE, rho g dz minus rho a half v squared equals 0, because we got rid of this term here. And if we choose to integrate these terms, then what we end up with is that this is equal to minus p minus rho g z minus rho over v squared over 2. And that, since we've integrated it, is plus a constant. And so this has to equal some arbitrary constant that we don't know. And usually the way that I remember it is exactly the way that's up here. And so if you divide both sides through by, let's do a different color. It's getting very colorful. If you divide both sides through by rho g, doesn't matter that this is still constant. And so we end up with the final expression is, and we get rid of these because we don't care that it's positive or negative. We just end up with p over rho g, which I always write as unit weight, elevation, plus, we get rid of this, v squared over 2g equals some different constant. And that's Bernoulli's equation. So we could have given you a long-winded derivation, but ultimately our interest in this is probably in using it rather than deriving it. But it's useful, I think, to realize that it really comes from just this expression, which we've used to define what the pressures are in a static volume. And it applies if that volume is moving. So what we could do, if this is true in one static volume here, it's also true in another static volume that exists on this same streamline. And so this is now true as you go from an upstream location to a downstream location, flowing in the direction, and the velocity has to be a streamline velocity in this direction. And typically the way that we use this is that since we know it's constant, then we can merely write it in terms of an upstream value where we know some of these three terms, a downstream value that exists along the same streamline, say at point 1 and point 2, and then we try and figure out whether we have enough information to solve these 6 unknowns in our equation for the one unknown that we have. And we'll find out that typically we can do that. In some cases where we have 2 unknowns, we have to have another constraint, which is a volume change constraint, which we'll use in due course, but that's basically how we'll do that. So that's Bernoulli's equation. So that's an important equation. It's important to realize that the velocity that we're talking about is always along the streamline. So it's the velocity which is in this direction at point 1 and in this direction at point 2 rather. Importantly, you'll realize that since these are streamlines that represent the streak of the fluid through the system, the velocity that's orthogonal to this has to be 0, right? Because there's no effect. The maximum velocity is along the streamline, and so there's no velocity of the fluid in the orthogonal direction. So it's always the streamline velocity that we're interested in. So that's basically Bernoulli's equation. You see it here written slightly differently. You can write it in its differential form. We've used z for the direction, but it's really a distance s along the streamline. We've taken a liberty with what we've done because we've derived it a little bit simplistically from the idea of our static fluid, but basically we have the expression that allows us to define behavior. Importantly, though, we know, and this is what I always tell people who come up to me, I don't have prerequisites for this. Do I need Math 251 and do I need EMEC or Physics 221? The only thing you need for this class, everything we do is basically based on this one expression. Newton's second law, force equals mass times acceleration. And in the same way as we solved that for static fluids, Bernoulli equation is a manifestation, if you like, for the moving case. The requirements to apply the Bernoulli equation in this simple form are that the fluid should be incompressible, which is okay. Air is not incompressible at all. Of course, nothing is incompressible. Some things are more compressible than others. Air is much more compressible, as we know, than water. But typically, Bernoulli is used just fine for calculating forces on airfoils in air. And so air is usually okay, even though air is not really an incompressible fluid, so long as the pressure changes aren't so big. The fluid flow should be irrotational in that there shouldn't be vortices set up like you get on wings that roll off sometimes at the edge of wings. If you look at a commercial airliner, it has these winglets on the end of the plane. Those are to stop the vortices rolling off and losing energy. And so the flow should be irrotational. It should be steady state. And so that's an important one. And so that basically means that if you look at, say, flow over a weir, then certainly the velocity that you have at this point is probably different from the velocity at this point. But the velocity here, although it's replaced by more new molecules coming from upstream every single instant, the velocity is not changing. So it's new water that's flowing through here, but the water here, if you look at time 0 and 10 minutes later, it's still flowing with the same velocity. Likewise for this is a different velocity, but it's not changing in time. So steady flow means that it shouldn't be changing in time. And so that's kind of important because it depends on your reference frame. And we'll talk about reference frames later, but you can imagine that if you're sitting in an airplane and you're looking out at the wing to your left, if you're in a window seat, you can look at the leading edge of the wing and there's some velocity. Look at the trailing edge of the wing, there's a different velocity, but that's not changing very much. If you're a static observer and you see the plane moving past you, of course, that's not steady state. So it relies on the frame of reference, I guess, that you use to be able to do this. And so that's important. Interestingly enough, for many of the things that some of the people in this class would be involved in, petroleum engineers, environmental systems engineers, when you look at flow within the subsurface, it can be steady, but typically that violates the last of the requirements, and perhaps the most important requirement of the Bernoulli's equation, which is it has to be inviscid. There's no viscosity. In other words, the viscosity of the fluid should essentially go to zero. And physically what that means, of course that isn't true for any fluid. There are no clearly frictionless fluids, but what it means is that there's no energy losses in the system. When you flow from the pipe upstream to downstream, you have the same pressure delivered downstream as upstream. There are no frictional losses along the side of the pipe. That would be a viscous flow. If there are not losses, then it would be inviscid, and you could use Bernoulli's equation. It turns out that many of the problems that we'd like to solve, the essence of the problem, such as the configuration of flow in groundwater, is the viscous losses in the system, which is manifest in Darcy's Law, if you know what that is. But that does not satisfy Bernoulli's equation. Okay? So, that is, we avoided doing all of these differentials in terms of what we wanted to get, and we ended up at this point here. So I'll just spend a little bit of time maybe talking about this. We've talked primarily in terms of flow along a streamline. We'll talk separately about going across the streamline. Most of the time we'll use this expression in its non-differential form. I find it by far the easiest to use it in this form, so that we lose these terms. And to realize that if it's constant, we can write the equation at two individual locations. So the physical meaning of this, I guess, if we try and look at it in terms of behavior, it's not written quite the way I'd like. We know that this is, well, what are these terms called? This is called pressure head. It's two words. This is called elevation head. And this is called, for want of a better term, velocity head. Not really. Or dynamic component. And so in static fluids, and actually also in flowing fluids, it's useful to try and think about what these components are. What we can define is something called an energy grade line. Which we will identify later. But the fact that this magnitude is constant means that if somewhere on a streamline that's flowing, let me do it in green just so it's consistent, a streamline that is flowing, say, along here. Let's do a streamline that parallels this particular streamline. And the point is that upstream at this location here, clearly if we take some arbitrary datum, it could be anywhere, we can choose it anywhere, could be above our system, could be way below it, then the fact that this is constant means that if we measure this potential, the units of which are all in units of length, so in SI units, it's easier to see this because this is in units of length. This has to be in units of length. What are the units? Pressure is in units of newtons per meter squared. Unit weight is in terms of newtons per meter cubed. And so by definition, they all have to be in those same terms, and you can do the same for this as well, is that the sum of these three components add up to the same amount upstream as they do downstream, because we're not losing any energy in the system. If we were losing energy in the system, we'd have to have another term in here, which is equal to head losses. And we won't do that now. We'll get to that when we talk about pipe flow, where the essence of pipe flow is the fact that you lose energy as you flow from upstream to downstream. So if we look at what we expect this profile to look like here, then we could physically draw our pressure distribution with depth. I guess I didn't need to do it to the bottom here, but if you wanted to calculate the pressure at this point here, it's just going to be equal to this same expression that we've used before. dP dz is equal to minus the unit weight, and we know that when we integrate that, we get something like the pressure is equal to P0 plus gamma. I don't want to use Z, but I guess I should use H, right? And so physically, this height here is H, and it's this term. And so if you put a pipe into this that was facing downwards, so that the velocity going across the bottom is still going across the bottom, the height rise in this pipe would come up to the surface here, where the atmospheric pressure is 0 in the pipe and also 0 in the fluid around it. And we know that because we could rationalize it that if the pipe looked like this. Oops, I didn't want to do that. Oops. Right, squirrel, didn't want to do that either. Okay. So we know that if we made a pipe that went down to this point here that looked like this, the rise in it would be up to here, because we know that if we go from this point here, atmospheric, all the way down here and back up here, then we know that the pressures have to be the same, because we've just gone horizontally. And so this would be the height rise that would occur if the base of the pipe is flat and the water is just going across the base. If, however, the pipe is facing upwards, then what's different here is that the fluid going across this base is going at this magnitude of velocity v1, which is just the velocity of flow here. Here, as it hits this pipe, by definition, this velocity v1 has to go to 0, so-called stagnation. It's coming up against this pipe, happily going downstream, bam! It hits this orifice. It doesn't go in, it stops, because it has other fluid that's just in the pipe, which isn't going anywhere either, it's static, and it has to scoot around it to go downstream. And so the essence of taking a velocity, a small amount, a distance upstream of this, which is going at v1, and then right at the tip of this pipe, which is going at 0 velocity, is that you're basically killing this velocity. You're killing momentum. Mass times velocity, so we know that F equals ma, which is equal to mass times acceleration is mass times dv dt, which we know that we can write as dz dz. So this is basically a rate of change of momentum that's occurring within our system. And the rate of change of momentum is what gives you this velocity head that's here. So it is velocity head. I was blanking as to what we call it. Let's call it velocity head. So if you're upstream, you get a rise that's this because you're not killing the velocity. If you're impacting on this, you get a different magnitude here. As you go downstream, then still the conditions have to be that the total Bernoulli head has to be constant. You certainly know what the elevation is at this point. You may have to have a problem in trying to figuring out exactly what the distribution is between the velocity head and the pressure head if it's the downstream part of a weir. And we'll talk about that in due course. Okay? So that's kind of the important features of what we're dealing with. This is a useful example from the book just to illustrate a point. And the main point that they illustrate is that, or attempt to illustrate, is that you can define the behavior here in terms of these three components. So there's an elevation head, there's a pressure head, and there's a velocity head. We know that we can add these together, and it has to be equal to a constant. But if you look at these three different locations, and figure out what these individual components are, oops, then it's relatively straightforward, right? So at this point here, the elevation is low, and so the elevation head is quite small, and you could calculate it if you know where your datum is. I guess if this is your datum, then it's actually equal to 0. So I'm just going to draw columns under each of these terms. If you look at the pressure of this, then it's enclosed, you're squeezing it, and so the pressure is quite high. And if you look at the velocity here, well, it is moving. It's actually moving because the plunger perhaps is moving slowly, but it's either very slow or 0, depending on how you want to define it. If you look at the nozzle, as the fluid comes out of the nozzle, we know that the pressure in the x direction has to equal the pressure in the y direction, which equals the pressure in the z direction. We know that atmospheric pressure has to be acting here, and so as it comes out of here, immediately past the nozzle, typically we'll assume that the pressure is 0. And so this would be atmospheric pressure. So this would be atmos, or 0. But now it's squeezing out of here, and it's being pushed out, and it's going quite quickly. So this term is large. And I suppose it's moved up a certain amount, so this term has increased a little bit, but not very much. And finally, it goes up to the top. It reaches the peak of its climb. Actually, what you'd find is that if you look at the magnitude of the pressure just inside here before it comes out, this height here would be given by P equals gamma H. So the pressure just inside this nozzle would be equal to the height of this rise, just as if it was a static column. And we'll talk about that later. And so if you look here, the pressure at this point is going to be equal to 0 also, because it's atmospheric. The velocity, well, it's gone up and it's stopped. And so the velocity should be 0. But its elevation should be a big number. In this case, it's whatever h is. And you look at the bottom, you'll see the same things. So it's just looking at so these are 3 forms of energy that you have in the system. Potential energy, pressure energy, and kinetic energy. And they're getting exchanged within the system as you move through it. Okay? So that's all really Bernoulli's equation is saying to us. All right. I don't know if we have time for it, but I was going to do this, and I was going to come back to this video of this. And so how would we use this to make this calculation? Is that too late? So we can use Bernoulli to do a very simple calculation to be able to say how that works. And the straightforward way of doing that, if you wish, is to just use Bernoulli's equation. So let's see if we have time to do a quick example. Let's kill this. And so let's try this. And so we have a jet engine. Air comes in through here, goes out through here. I won't draw it in, it should be in profile, of course, but the basic requirements for this are that, one, we can define behaviors at 2 locations along the streamlines. Location 1 and location 2. We could choose other locations, but those might not be so helpful to us. We can write Bernoulli's equation for each of those locations. We can equate them because they are equal to a constant, upstream and downstream. And we can look at the particular conditions that we have in our given system. What do we know? This is xy, this is z, San Francisco is basically a mud flat. Often runways are quite flat, right? So these two are equal to each other. Not necessarily zero, but they're equal to each other, so we can get rid of them. This has just come outside of the jet engine. The same arguments with the syringe as it comes out. Pressure's acting atmospherically around it. Let's work in gauge pressure, where this is 0, and this actually is 0. I guess these two here are just equal to each other, right? And we know that when it hits here, the streamline velocity is whatever it is turned to 0. And so we have a very simple equation, which is just this. Let me do this. Makes it simpler, right? And so if we wanted to, we could write the pressure at point 2 is equal to rho V1 squared over 2G, over 2. Right? And hopefully that should have the right dimensions. And so what we're calculating is the pressure that's applied on the side of this truck. This is P2. This has some area A2. And what do we know? We know that in perfect flight, not at takeoff, the air that's coming out of here would be coming out at 500 miles an hour. I don't know if that's true. Maybe it's coming out at, let me take 200 miles an hour. That's typically the speed that you need to get up in the air. So maybe at full thrust is that. And you'll find out later that for a plane going at 500 miles an hour, gas has to be coming out of the jet engines at that same speed. So if you know that this velocity is 500 miles an hour, 200 miles an hour, I chose that because that is equal to about 100 meters a second. It's a factor of 2. And so if you want to calculate the pressure that's applied on the side of this vehicle, density of air is about 1 kilogram per cubic meter. The velocity is equal to 100 meters squared. Have I lost something here? To be rho v squared. Yeah, okay, rho v squared. And so if we multiply these together, are those the right dimensions? V squared over 2g, p over gamma, which is rho g. G's go out. Okay. Then we end up with where's the acceleration term in this that we should have? Do we get rid of both g's? Yes, square root. V squared, that's the acceleration term there. So this is squared. So it's 10 to the 2 times 10 to the, this is 10 to the 4. This is newtons per meter squared, thank you, which is equal to 10 kPa. Is that right? Missing a 0. So squared, that's 3, right? Missing a 0. But that is right, yeah. So it's 10 kPa. Oh, there's a 2 in there as well. Thank you. Is that right then? So you could calculate from that, if you know now what the area is. I guess one simple calculation, I think that's about of the right order of magnitude. And so if you wanted to look at the stability of this, then you could, for instance, look at just rotational stability about some point with the weight of this truck. I looked up what an F-150 should be, and it was something like 30 kilonewtons. in terms of weight. And so you can just do this, the math that P2 multiplied by A2 multiplied by some lever arm, say 1 meter, is equal to W times some lever arm, which is equal to, say, 1 meter also. And so if you know the weight, which is equal to 30 kilonewtons, if you know the area, side of a truck, 10 feet long, 3 feet high, that's 3 meters, 3 square meters. And you know that the pressure that's being applied is something like 5 kPa. So this term is 15, this is 30, so it roughly makes sense that at least to the order of magnitude, the forces that you're talking about in this particular case are the ones that you'd require to be able to have some overturning around the wheel, which is in this corner. Basically, that's what we're saying. Okay? Thanks for the help. So that's Bernoulli's equation. Please do look at the review stuff very quickly. Bring your questions on Friday. We'll talk about it briefly and then move on to talk about Bernoulli some more. Okay.